So let's start this video by trying to work out how we can graph the function, say y is some function of x, and this particular function of x is going to be equal to the sine of x. So we're trying to graph y equals the sine of x. So how do we graph any function? Well, a good way to start would be with a table of values. So let's come down here and we'll have our input and our output. Okay, and we're going to do a table of values, and I'm going to start at 0 degrees, we'll go to 90 degrees, 180 degrees, 270 degrees, and then 360 degrees as well. So let's see if I put these numbers for x into my function, what outputs I get, and that gives me a table of values which I can then start to plot. So when x is 0 degrees, so the sine of 0 degrees is just 0. The sine of 90 degrees, that's equal to 1. The sine of 180 degrees is equal to 0. The sine of 270 degrees is minus 1. And the sine of 360 degrees is 0 again. And in fact, this is the end of our unit circle. Okay, so if I was to go anywhere past 360 degrees, I'm just going to start going around that circle again. So I'd be going back to the start here and just working my way back along if I was to go any further out in this direction. So let's just sort of zoom in on this 0 to 360 degree portion, and let's start to sort of graph this and see what maybe it looks like. So if I take my y-axis and my x-axis, and of course we've got our point 0 here, we've got our 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Okay, and we're going from 1 is our highest point in this table of values to minus 1 being our lowest point in this table of values, and of course this point here is 0. So let's start by plotting these points which we've generated in our table of values here. So I get the point 0, 0, so that would be here. I get the point 91, and then I get 180 degrees, I'm back to 0 again. 270 degrees, I come down to -1, and 360 degrees, I'm back to 0. So we're starting to kind of see this like almost thing that's going to cycle around. And in fact, if I connected these dots, we kind of see this shape happening. Okay, and we know that because I just got to the end of my unit circle, if I was to continue here, this would just continue off in the same sort of direction. Okay, and this is sort of our first guesstimate to what a y equals sine of x looks like. Now we're not quite there yet. We haven't quite plotted what the sine of x looks like. We're going to need to do a little bit more. And the way that we're going to do that is I want to zoom in to this portion here. Okay, I want to zoom into this 0 to 90 degree portion. So how we're going to do that is we're going to create another table of values over on this side. And we've got our 0 degrees up to our 90 degrees. But there's a few more points that I want to pop in this time. I'll just zoom out a little bit. We're going to zoom in here. So I'm going to have my 30 degrees, my 45 degrees, and my 60 degrees. So we're kind of zooming into this little space that I've circled in yellow here. So what is the sine of 0 degrees? I get 0, and 90 degrees I get 1. Now let's look at the behavior in between this point. So sort of the behavior that's happening in this space, in this yellow space. So sine of 30 degrees, well, we know that that's a half. Sine of 45 degrees, that is the square root of 2 over 2, and the sine of 60 degrees is the square root of 3 over 2. Now, if I convert those to decimals, I get 0, I get 0.5, I get about 0.7, 0.87, and then I get to 1. So what I'm seeing is that from 0 degrees to 30 degrees, maybe 30 degrees lies about here, what's actually happening is I'm already up to a half. Okay, so very quickly, I've already got up to a half here. So say this is at 0.5, I'm already up to this point by 30 degrees. And then it's a slow, steady climb at 60 degrees, or at 45 degrees, 60 degrees, and 90 degrees. It's a slow, steady climb over a longer period of time to get to the top. So what I actually see happen for a sine function, okay, is I get this more sort of curved shape, which I'll do in purple here. So we kind of come up, we come back down, and we're curving like this. Okay, so the actual function for sine, and maybe we'll just come down and we'll redraw that again. Okay, so I've got my, so we've kind of proved it all now, how this works. I've got 0, I've got 1, I've got -1, I've got 90 degrees, I've got 180 degrees, I've got 270 degrees, and I've got 360 degrees. And my first sort of thought was that this was just going to be straight lines. But what I saw when I zoomed into a particular section was that this thing is actually going to curve a little bit, and it does so like that. And that is what we call one cycle, okay? Because as we saw, if I just continue around this unit circle, this thing will just continue to cycle off into the distance, okay? And it's just going to continue to repeat itself the more laps it does around a unit circle. So this sort of image here, this is what I want you to remember, okay? We've got to remember this. This is what a standard y equals sine of x looks like. And if you can remember that, then you'll be okay for the rest of these videos to come about these sine functions, okay? So this, in the purple there, that is what one typical y equals sine of x sort of curve looks like. What we're going to have a look at now is what we call the amplitude and the period of our functions. So we'll start with the period, okay? So the period is the time taken, so the time taken to complete one cycle. So what we mean by that, the time taken to complete one cycle for a sine function is how far we go until we start to repeat ourselves again. So we start to repeat ourselves here once we've done a full lap around that unit circle. Okay, so that's one cycle, which I've done in the yellow there, and we can see that that takes us 360 degrees of time, if you like. So in this particular case, the period here would be equal to 360 degrees because that's the time it takes to complete one cycle. So hopefully that makes some sense about what the period is, okay? It's the time that it takes to complete one cycle. And as sine function, that thing just cycles through as we go around that unit circle. What we're going to have a look at now is I've got some different graphs here, and we're going to try and work out what the period is. So let's start with this red one, it's the exact same function as what we're actually looking at, okay? It's y equals the sine of x. And I can see that if I say I start at this point, I keep going along until, how long does it take me to get to the same point that I started at? Well, that happens here, okay? That's when I'm going to continue to cycle round and get the exact same sort of portion. So how long does it take me to complete that cycle? Well, I can see that that takes me from 0 to 360 degrees. So that period there, okay, is going to be 360 degrees. That's the sort of the time, if you like, that it takes to complete that cycle. But I don't have to start there. I could start somewhere different, okay? If I use a different colored highlighter, maybe I use a blue highlighter here. I could start over here if I wanted to, right? So I could start there and I could cycle around until I get to that same point that I'm starting at. So that would be up and around here somewhere. So that would be me going from 135 to 495. So if I wanted to do it that way, it would be unnecessarily complicated, but the period here would be equal to, again, 495 minus 135, and we see that that is 360 degrees. So it doesn't matter which sort of section you choose to take to repeat itself, the period will still be the same. Okay, so it's easier to start from 0 though, because you can just read the period straight off the page without needing to do any subtractions. If we come down here and we have a look at the blue one, so I'll go back to my yellow highlighter now. How long does it take to complete one cycle here? Well, I'll start at this sort of point at 0, and we go up and down and back up again. I finish that cycle there at 180 degrees. So the period for this blue function is actually 180 degrees. I can pick this guy in yellow up and I can continue to stack him widthways to sort of create the rest of this blue function here. So that would be another portion there, and I could draw another portion in if I wanted to. I could use a sort of a pink one and I could put another cycle in, and you can see that they're all the exact same sort of piece, if you like. I'm just stacking them up. Okay, and each piece takes 360 degrees, 180 degrees in this case to complete itself. So the period for this bottom one would be 180 degrees. I've got two more which we can look at to try and work out what the period of these functions is. So we'll take our yellow pen again. So this one here in the green, I start here at 0, I come up and down, and I go back up again, and you can see I'm sort of finishing in this space here, and it's actually kind of hard to tell exactly where that point would be. So what's another way that I could tackle this? Well, let's continue to put in more pieces. So I'll put another piece into here like so. So there's another piece there, and I'll do a third one, and you'll see that when I do the third one, I hit a perfect point of 360 degrees. So why is that important? Well, that tells me that I get 3 cycles in 360 degrees, which means that one cycle would have to be done in 120 degrees. So I see that the period for this green one would be 120 degrees. So I can't quite tell exactly what point that is, okay? I don't know whether it's 120 degrees or maybe 110 degrees. It's kind of tricky to tell because I don't have those axis lines. But if I put a few cycles in and I see that I then intersect at 360 degrees, I can use this method over here where I kind of say, okay, well, I do 3 cycles in 360, which means I get 1 cycle done in 120. And finally, this last one, we'll use our yellow pen again. Okay, I start here and I do my cycle. I actually only get 1 cycle done in this graph, okay, in the bit that we're looking at, and that cycle takes 720 degrees to complete here. So I see that the period for this particular graph would be 720 degrees. So hopefully that makes some sense about what the period of a sine function is. Okay, so what we're going to do now is we're going to come down here and we're going to have a look at something that we call the amplitude. Okay, so that's another property that goes alongside the period, which is really important for these sine functions. So here I've got a few different sine functions which we can have a look at, okay? And I feel the amplitude, kind of like the period, it's better to sort of understand if you just see a few examples. Trying to sort of define it and then trying to read that definition and understand it is nowhere near as easy as kind of just looking at a few practice problems. So the amplitude, we're kind of looking at the difference in height. So you can see that that one in there, red, is a lot different in height to this one here in blue. The blue one's a lot taller, and the green one is even taller again, okay? And just being careful of our axis, we see that we're going up to 1 here, up to 2 here, and we're going all the way up to 3 here. So what is the amplitude? Well, the amplitude is the distance sort of from halfway to the top. So what is our halfway point for this red function? What do I mean by that? Well, kind of see how if I draw this yellow highlight line, that is splitting this function kind of in half, okay? We can go 1 in this direction, or we can go 1 in this direction to our lowest point. And we kind of see that this line here is our lowest point that this function goes, and this line here is the highest point that this function goes. So we're going from 0 up to 1 or up to -1. So the amplitude in this case, okay, the amplitude is equal to 1. And the amplitude will always be positive. That's important to keep in mind as well, okay? It's just a magnitude of the value from the distance from this line of symmetry, this kind of halfway point, the distance from there to either the top point or the bottom point. Both of those distances will be the same. So for example, this blue one here, if I get my yellow pen out again and we draw the sort of the halfway line, which runs directly along that axis there, okay, if I was to look at the distance, the highest point it can go all the way up 2 units up that way, and the lowest point it can go is down 2 units this way. So the amplitude for this blue one, amplitude is equal to 2. And then this green one, if I was to come over here and I draw my sort of my halfway line, so that's halfway there, and again I should see that the distance to the top is the same as the distance to the bottom, okay? And it is in this case. We go 3 to the top, we see 3 there, and we go 3 to the bottom, you see -3 there, and we're coming off of our 0 line. Okay, so the amplitude in this case, amplitude is going to be equal to 3. Where the amplitude can start to get a little bit tricky, okay, is when we're no longer sitting at our halfway line, sort of being at 0, okay? What if we start to move this function up or down? So I've got a few graphs which we can have a look at here, and you'll see what I mean. So here, where does our halfway line sit? Well, it no longer sits at 0. Our halfway line is actually going sort of along here, like this. And what do I see in terms of the distance to the top in comparison to the distance to the bottom? Well, I'm going from 1 to 0, so that's a distance of 1, and I'm going from 1 to 2, so that's also a distance of 1. So this one here actually has an amplitude of 1. Even though you kind of look up here and you see this 2, that doesn't mean it's got an amplitude of 2. That's still got an amplitude of only 1. What about this one down here in blue? Now we can see that this has got a smaller period, okay? It's cycling through a lot quicker, but that has no impact on our amplitude. Again, for the amplitude, we're just looking to find our halfway line, which is that line there. Okay, we're going from -2 to our tallest point, so if we're to come up here, -2 to 0, and our lowest point going from -2 to 4. So what's the distance traveled there? 2 up here and 2 down here. So this one has an amplitude equal to 2. Again, our amplitudes can never be negative, they can only be positive, and it's just a magnitude of measure of basically how tall our function is. So hopefully that makes sense about amplitude and period, okay, and also about what a sine function actually looks like. You've kind of got to remember this basic shape here for the sine function, which I'll just go through again in that blue pen. We loop over like that over a 360-degree period for just our standard y equals the sine of x.